Okay, so welcome to today's session. I'm just going to be carrying on with the slides. So what I'm going to look at in today's session, we're going to look at the modeling, techniques for modeling motion inside of Autodesk Inventor. So my name, as you can see at the bottom right, is Tashis. I've been with the CAD Corporation for about 4 years now, and I'm on the manufacturing team where we specialize mainly as our core product on Autodesk Inventor, as well as all the other products then within the product design suite. So if you do have any kind of questions even after the session, please do post them to me, or even find my email address now on the right-hand side if you do want to send any kind of information to me or request some support even from our side to assist you with anything that you need. Okay, so getting started with this, what I want to speak about as quickly as what we're going to be covering in the session. We are going to try and see if we can get it finished. Obviously, with the delayed time, I do apologize if we need to go. But let's carry on with this now anyway. So as a summary, what we're going to be covering is this class will walk through how to model motion inside of the assemblies within Inventor, and also looking at the different characteristics that we'll use to go and do those kind of connections, using different constraints, joints, using the context solver, and also driving those constraints using the drive tools. So you might have used some of these before, but that's why we're going to try and cover them so you get the basic idea of how we can generate motion within those assemblies. Okay, so the key areas we're going to be looking at today is understanding differences between constraints and joints. Now, this is something that you should have probably seen already in older versions. 2014 introduced us to the joints, and also in there they introduced a new constraint as well with the symmetry. Obviously, symmetry not having an aid for us specifically in motion, but we can also use that to incorporate motion into that same similar symmetry constraints. But we're also going to look at how to drive those constraints once we set them up. Also seeing how the context solver itself will allow us to limit motion, also do some kind of analysis regarding clash detection. We also wanted to then look at some of the more advanced motion tools that we see within the actual constraint dialog box. Things you might never have considered or used before. So it'll be nice to see how those things work as well. And then finally, within an assembly level, we're going to look at the flexibility that when it's enabled, we can actually move sub-assemblies constraints at the same time while we actually move things within the higher level assembly. Okay, so just a quick little heads up of who we are. I'm just going to really quickly ramble over this. CAD Corporation with our headquarters sitting here in Centurion. We have multiple offices sitting in different locations, so in Sandton, Boksburg, Cape Town, and Durban. We are level 3 BBB, triple BEE contributor as well. So if that is some form of requirement, you can also see that, as well as then what we also are accredited for, being in the AEC field, the manufacturing field, PIM field, and finally infrastructure as well. Okay, so getting started. The introduction of what we just want to do here is we see that within modeling an Inventor, a lot of our designs focus on moving components. We also see that we sometimes have positional changes that are required to test and see for certain things and how they basically interact with other objects. So making sure that we set up the correct limits of a component's position and movement that it can be created in. We also look at how assembled components have to fit together, even by just modeling them up in a kind of sketched environment to see this component needs to sit in this specific reference and the next in the other reference. I mean, there's already some positional change between them, so that if I need to toggle an open and close position, I can immediately do that within an assembly level. This is also sometimes part of a manufacturing process, so being able to see if you're designing tooling, what is the maximum and minimum position of things can move, to see if whatever you're trying to generate will be able to fit within those tolerances as well. And then finally, the time and comfort, being able to use the CAD tools to restrict the modeling in motion, so you don't have components sitting all around the show. You position them exactly where you want them with their degrees of freedom still available that you need for movement. Okay, and basically also with this, we also have the different methods that we can use now to examine those motions within the CAD model. Now, with degrees of freedom being mentioned, for those of you who don't understand it, or maybe have a basic idea of it or how Inventor represents it, we see these images on the right-hand side. You might have seen them before when you enable the actual viewing of degrees of freedom. Now, this over here will allow us to see that we have 6 different degrees of freedom. 3 on a linear level, and 3 on a rotational level. Now, linear, meaning it can move in X, Y, and Z directions, and rotations mean it can rotate around those specific axes. Now, these markers you can basically enable on a part level, on an assembly level, or on a higher end assembly level with multiple sub-assemblies to see how all of the components together can move within the main assembly. Okay, and this is just basically something that you can view. It's not something you can specifically use or click on, but when you're starting to apply constraints, these will immediately start limiting themselves with the degrees that you remove. So if I put a mate and a mate constraint together, it allows me to basically limit a transitional change, and even at certain points, it can even change a rotational degree of freedom as well, depending on what I mate or constrain together. Okay, we'll look at those as well as we go through the actual modeling to see how we can actually use that within the motion side of the assemblies. Okay, then finally the topic that we are all wanting to look at, especially if you haven't used this tool before or you've looked at joints, but as soon as you click on it and apply it, it doesn't do exactly what you want it to do. Now, I'll explain a couple of the advantages with joints, which is very, very useful, and I'll also show you exactly how we go about using those. Because it's very good for us to know how we can apply these different types of techniques, when to use joints, when to use constraints. Now, basically the constraints from the beginning of Inventor, when you started using it, that was our method of being able to connect components together. So it's a standard method. It also helps you define components that are fixed together. It also, as we start applying those different constraints, we start removing those degrees of freedom that we spoke about earlier. But if you don't put in all of your constraints, what it will allow for you to do is to still have some form of motion allowed, and you'll see that if you have your degrees of freedom visible. Alternatively, by just simply left-clicking and dragging around, you'll also see what components can still freely move. Now, joints, on the other hand, is a different method of using the similar constraints we are used to, but they're already defined from a preset list. There are rigid constraints, rotational constraints, slider constraints, cylindrical constraints, planar constraints, and finally ball constraints, or should I say joints, sorry, that will allow us to go and limit our specific movement between components along those specific degrees of freedom. For example, which we'll look at a bit later, rotational joint will allow for us to only have a degree of freedom which allows for rotation. There'll be no linear movements along any of the axes. Just one will allow for rotation around it. Then we have things like the slider, which will allow for us to go and move between two directional areas, so two different linear translations, but also, once again, not being able to move up in a vertical direction. Cylindrical is one translation, one rotation, and ball, for example, no translation, but in all areas it can rotate in all three axes. Now, with these joints, what we have is we also now have an easier way to select exactly how we want to connect components, because it defines from a specific point or location to connect to another component's specific point or location. And when we define that specific type of joint, we don't have to go and say, use this as a mate, use this as a flush, or any kind of insert constraint methods. It'll automatically apply the one it assumes, or you can choose your specific type of joint that you would then define for that movement. Now, when we apply all of these constraints or joints, the degrees of freedom are removed, which means that they limit the movement between the setup that we want. Now, in the same way, there are different things we can do with this. For constraints and for joints, we can apply what we call limits. Now, these limits will allow for us to go and define a starting, meaning a minimum, and a maximum position for the movement in which you can move it, which means we don't remove all the degrees of freedom. We can limit the remaining degrees of freedom within those limits. So, as the example on the picture on the constraint side at the bottom, you'll see that there is a minimum and maximum allowed for certain objects. So if I had to make two faces apart, I can say the minimum distance and the maximum distance is indicated over here, which means the only travel that's allowed is between those two values. Now, these are things that we can easily set to try and limit positions, especially when you go and create drawings, because you'll see over there that we'll also look at, there's a resting position, which we can define. So that if you want to indicate this on a drawing very quickly to move it back to its original position, it'll always bounce back to that resting position. So always know that the representation we want to view is going to be from resting position. Now, we can basically define that and update that based on components. and multiple components could have this built into each of their constraints. Now, from a joint side, we have a very similar tool, but we won't have something that we have as an offset as a resting position, but we'll have a default one or center one or current one, which means at this point now, I want this to move to this position, even though you have a minimum maximum, set it to a current value. Now, you'll see with that when I use these joints, there are other things we have to look at, specifically called the teardrop to see your alignment, how to align specific components together. And we also get to see that this can be used then to make sure that our position that we wanted to align with is already set from the beginning. Okay, we can toggle them left, right, or out, inside, outside. Okay, so what I want to do now is I want to quickly show you a bit of a demonstration on this and see how exactly we can go and use this information using a specific setup. So as you guys will know, I'm opening Inventor 2016. This is the current version. There would be no updates regarding these tools between 2015 and 2016. In 2014, there were slight changes to the 2015 with these different styles. But what I want to do now is I'm going to quickly show you how we can use joints to actually insert components. So over here, what I'm going to do, I'm going to open up an assembly back and quickly go and disassemble some components to show you how we can use the tool. Now, with the hover press that we have open over here, I'm going to basically dismantle some of these components and then use the joint and relate it to how we could have used it using the constraint tools and see the similarity and differences between them. So if I had to take this component over here and I want to now still fix it around this specific pin, normally what you could have done is say constraint, use an insert constraint to specifically specify a reference edge to another reference edge to make sure that it's not fitted over here. Okay, that was one of the tools we could have done before. But now using joints, if I just select something very similar, and you'll probably see this when you go and use joints for yourself, is it tries to look at specific points that could be useful within the model. So if I look at this, I can find perpendicular, or should I say tangent edges with their points of where there is tangency on the specific face. I can find center points within arcs. So if I hover over any arc, I can find a center point on either face, but also midpoint between lines, as you can see as well, across different faces. So on this face, I can go and select that one, or I can go and select it on this point anywhere along here. Now, what this means is we can go and choose already the type of positioning we want with the joints. So if I wanted this to be automatically solved for me, so it'll probably end up with something like rotational if I select a cylindrical reference and another cylindrical reference. If I want to set it rigid so it cannot move, I will go and choose it even now. But I want to show you what the automatic does first off. Selecting this reference right here in the center, and the order of selection is necessary because if I select a grounded component or a fixed component, it'll want to move the fixed component and give me the warning that it's going to say it's going to move the fixed component to the actual component that I want to move to that side. So now I'm selecting the moving component first, which is the correct way to move it then to the new location. And when I move it there, we already see that it's trying to build in a rotational joint. Now this preview will always play when you go and use your different joints, which means you can always reanimate them if you do want to. But if it irritates you and you see it too often, you can even work fast and it probably won't even pick up that it's still moving. But you can also disable this automatic playing over here, so it doesn't play it by default when you put these in. Now, in this case, the alignment itself is wrong. So if I had to just switch this across quickly, you'll see that I can toggle this also from top to bottom, but it's still able to rotate. If I wanted to stop that, I can say, look, I want to align with this arrow over here, this face with that face. And now it knows that this is the resting position. And now I want it to stop moving to make it a rigid connection. When I apply these things, you see that it's trying to move, but it cannot, and that's why the vibration is visible. So if I had to say OK to this, nothing will be able to still move. So with this type of joint, immediately with one connection, I've set up the connection of how I want this to exist. Meaning I didn't have to go and make two faces and then look for a center plane to align with this one or use an angle constraint. I could have basically just done this now with one different or one now joint, which is now called rigid. And what's nice about this, you can always toggle between it if you realize that there should have been a different degree of freedom. Let's quickly put that on so you can get to see what I mean by the different degrees of freedom. So I'm just going to go and enable over here. Okay, let's just remember where this is now. Okay, I'll find this a bit later because the idea is I just wanted to show you how we can go and view. Sorry, this over here by view. Degrees of freedom to show currently what things can move in different locations. But this component itself, because I've now set this up that it cannot move, this that you see over here is the pin in the center. Okay, which means if I had to go and set the same kind of connection between this to the center over here, I can also see that I'm going to be removing these degrees of freedom. So I'm going to show you quickly how this would work. If I had to just go and align with this to that top side over there, I can change it once again to a rigid connection, which means it cannot move from that location. And then any existing constraints on this component will probably now override it, so I'm just going to have to delete those. So now any degree of freedom that used to be there is now been removed. Okay, so we can do things like this with these constraints, as well as when we want to realize that there should have been rotation allowed, you can just modify the existing one and change it to a different style. And immediately it'll update without us having to go and break or modify any existing constraints. Okay, so it's a very, very useful technique in order for us to go and assemble things together, specifically if you want your motion. Now, there is one thing that I did say before, which is existing constraints as well, is the limits. If I want the current value to be set to 0, you'll see that it restores its original position. This face is now aligned with that face. But if I want to put in these limits, I can say the limit for the starting point is 0, but it can only rotate up to 180 degrees. When I apply these limits, this movement can only go 180 degrees and back to the 0 point. It can't spin in any other direction. So if I had to show even a better example of this to make it say 90 or 45 degrees, you'll see even the limit being more visible. Okay, because I can only move now from 0 to 45 degrees. Now this same similar rotation story can also be set up when I go and use normal offset constraints. So what I'm going to look at here, because I don't want to show something specifically over here yet, I'm going to position this over here so that I can quickly align this using normal constraints for now. Okay, also quite a useful thing, offset predicting offsets. Okay, but what I want to do now is I'm going to quickly position this on the side over here, so that I can show you how we can go and constrain this position down here at the bottom so that a node can only move a specific distance. And once again, with the normal mate constraints, if I use them, if I mate this position to the base, I can look at this extended option to say I want to use specific limits. The offset value is sitting at 0, so let's go and use that as our resting position. So the minimum position that I can move is 0, but let's maximize this value to say 40 millimeters. Which means if I look at 40, just as an example, where it's sitting, it moves up to there. Maybe we can toggle this up a little bit more. Okay, so if I want this to be able to move up to here, we can probably push this up to about 80. So I'm going to put the offset back to 0. You can give it a name if you choose to. So we can go and say upward movement. And when I apply something like this, I can see the actual constraint and then just position it, and that is the maximum travel that it can have. Goes to 0 at the resting at the bottom, and then maximum at the top. As soon as I let go with my mouse, it'll immediately drop back to resting position. Okay, which is once again useful if we want to do things like our drawings. Okay, so basically with the joint side, we can really predict a certain couple of offsets and certain changes. And also what we can do with that is we can look and see exactly how to fit things together in a different method that we've used within constraints. Okay, but now we want to look at a bit more of the advanced constraint tools, because we looked at mate, we've touched on insert, there are a couple of other things like angular constraints, but now we're going to start looking at motion constraints. Now, some of you guys might have used this before, And within the specific motion one, you'll find that there are two options. We can rotate components relative to one another in a rotation-rotation constraint or a rotation-translation constraint. We'll look at both of those options to see exactly how it can influence the moving of the model. But in the exercise that I'll go through is just basically going to set up rotation with rotation. Now, the idea behind rotation is two components can spin together, but their rotations could also influence multiple other components as they move along. So the ratio that we're going to see up within here, the setup, will also affect how fast or how slow the alternative would rotate. Especially if you look at gears where we can have specific gear ratios, then we can set this motion between them using the actual ratio we'll be using over here. And we'll see that the rotation is relative to a full rotation of the first component that we select when we choose the two components. Then the second option over here is rotation translation, which also once again affects, in this case, the distance that a component should travel in one rotation of the circular object. Okay, but one of the objects will move in a linear direction, while the other one will rotate around its axis. Okay. Now, once again, selection order would be important, same with both of them. Spinning the component first, the spinning component will be selected first, the rotational one, whereas the second object, which will be linear travel, would be moved or selected second. One for rotation per offset movement. So let's quickly take a look and see how this works. So I'm going to open up Inventor again. Let's quickly look at a different example. Now, in this case, what I would like to look at is specifically the rollers that we look at over here. So I'm going to go and open up a specific roller, and I want to show you that when I rotate this specific object, they've already been positioned where they can move on their own, but not relative to the other objects. Okay, so they are all separate. If I want to be able to move together, what I can then do is go and generate this constraint, and inside the constraint options, I can simply go to the motion, and inside motion, I can select first object, which is the one that's going to be driving to its full rotation, and then I can go and select the second object, circular reference. It will find the center point to know if I rotate around its own axis, and when I say apply, you'll see that I'm going to let them spin in the same direction. When I apply this, very quick and easy, one rotation on this object will affect the rotation on the second. You see if there are no planes or interacting edges or faces that cause rotation, a simple reference using motion will allow us to go and connect them. On the third one, this one's maybe spin in the opposite direction, not for practicality, but just in this example. So if I had to go and create the same constraint with motion, I can select object A, object B to have opposing directions, reverse directions. When I say a rotation as if it was here, going forward, this one to go backwards. Okay, so we can also make sure that whatever connection direction we want will then be caused within this motion that we generate within the constraint. Okay, a modification here quickly. If I had to edit that same one and change the direction to the same direction, but maybe it's a smaller gear or smaller object, which means the rotation ratio should be 2. For every 2 rotations on this object, you'll see over here, when I apply this, it'll rotate at double speed, the connected object. Every full rotation over here, this one has to rotate twice. Okay, so that is basically using this motion constraint using 2 rotational objects. We'll look at the second one right at the end to see how we can use motion and translation at the same time. Okay, but this in itself can be used for anything that is cylindrical to make sure that an object rotates in a specific direction. Maybe a quick example is if I had to look at the other object, just close this one over here. I'm just going to open up this arbor press again. Now, motion translation over here, we could actually set this up very easily over here on this side if I had to quickly look at modifying this existing constraint, motion translation. Because in here, we can specify a specific distance an object needs to travel. So let's go and make this 78 mils. Okay, in a specific direction when the one object rotates. Now, in the same way, we can go and set up these limits if we had chosen to, but I want to show you here, if I move this object down, I'm allowing for it to move 78 mils before we have one full rotation on this object. So in a very similar way, if I had to just position this, I'm just going to go and delete this constraint. Go and constrain a mate constraint here at the bottom to make sure they are connected. Okay, this is now going to be basically the resting position. But all I wanted to do is just move it there. So if I apply this and just quickly go and close this down, or delete that actual constraint, we can even suppress it if we need to. It doesn't really matter. Because the idea behind this with that mate constraint was just to keep that position. So now I can go and relate this for rotation to this object. Using the similar way, constraining with motion, I can select the rotation option to say as this object over here rotates, let's go to use the cylindrical reference, then this object over here should move in a specific direction. So I'm going to set that direction over there on this object. Distance it should travel is maybe 80 mils for a full rotation, and we can go and choose specific direction, meaning if it rotates this way, it must move it up, rotate the other way, it must move it down. I can switch these if I need to. You'll see now, when I go and reposition this, the rotations being positioned like that. Okay. Now, to stop things like this, we'll also look a bit later on how to stop this from moving through the components, especially if we don't want them to continue rotating through themselves. Okay. Now, with these kind of constraints, one can suppress them if you want to. We can also modify them again or change them to different types as we would know before. So, what I want to do next then is being able to speak about advanced tools. There's a third option that we still have to look at within normal constraint, which is called transitional. Now, transitional means that we have a specific pocket in which a component should be able to move between, but never outside of it. Now, there is sometimes a bit of a problem with this one because it has to fit exactly. Otherwise, what happens is there's movement allowed between components. We can use this in conjunction with normal mate constraints or flush constraints or angle constraints to make sure the objects don't rotate in weird directions. But also they could sometimes, if they don't fit in the pocket exactly, they'll jump to the outside of the component, which means then we have to move it back into the center using the normal free move component before it'll then stay again in the center of the component. So it's not always the most advised one to use, but it works very nicely for different methods and different connections between components, unless it does break. Yeah, but let's really take a look at how this works. I'm going to go and open up a different component. Let's go and look at transition over here. Okay. Now, let's go and look at this object over here. So if I look at this, I want this object to sit nicely within this area. Now, to do this, the first thing I'll do is go and set a height level. I don't want this component to be able to move up and down or try and connect here because I want to show you what happens when I try this. Translation is very quick and easy to select. We'll select object A or B. In this case, selections doesn't really matter. But if I move it A to B, this now has to fit within that area. And you see that it's sliding and rotating and then all of a sudden jumping on the outsides of the object. It'll be terrible to try and work with something like this, which is why before I go and insert that constraint, I'll already set up some boundaries. I'll go and say that I want to make sure that there's maybe an offset between this face with the mate constraint to this one at say 50 mils. When I do that, it's already linear, so it's aligned, and I can now position it just briefly, roughly where I want it within this pocket, okay? Because when I do that, this translation constraint is already in place, and I can move it now freely within this pocket area, okay? But there are times when this jumps out, and then to get it back in there, we kind of have to suppress the translation, reposition, and then we can go and modify it again, okay? But if I didn't create this translation, as you'll see over here, I can still go move it roughly to here, and then I can go and insert that same translation constraint to make sure that the movement that this generates will still only be in this pocket area. Okay, you can still go and add in your constraints if you want this to always be perpendicular to this face or flush with that face. We can still put an angle constraint to make sure that takes place. Okay, because now I can move freely, but it always has to be flat on that face. Okay, so you can see it can't move out over there. Okay, so with translation, that was the alternative that we also had over here within the constraint tools, motion and translation, which allows us very nicely to go and make sure we can go and model something within motion to specify exactly where it can travel from and to. Okay, so what I want to look at there now is how do we drive constraints. Now, this is something that you might have gone through before in Essentials or taught yourself. When you look at a constraint, you can always drive it, meaning position it from point A to point B, but be able to push play to see how it actually moves. Now, there's a couple of nice things about this, which is nice for visual changes, but we also have some nice changes that can allow us to go and drive adaptivity. That's something we'll also look at a bit later on to make sure we can see how components can change in size when we actually start driving those components. So what I want to do in this case, if I jump back to any assembly like this, you'll always see that you have the option over here to drive specific constraints. Now, if I had to drive this angular constraint, all I have to do is right-click on that constraint and say drive. This in itself was already an angular constraint, so I can drive between rotations. I want to start at 0 degrees and end maybe at, say, 360 degrees, which will cause one full rotation. If I push play, you will see that it's going to be spinning around. Okay, because of the translation, you'll see that it's also moving in position. That is because it hasn't been locked down to any other defined position. If I want 2 rotations, I can move it to 720. And you'll see now that this rotation itself will continue for 2 full rotations, changing the position from point A to point B. Now, this in itself has more options. If we want to drive adaptivity, we'll look at that a bit later on. Collision detection can be toggled on and off. So if it does find any kind of collision, it'll stop at that rotation point and say collision detected. Okay. An object like this, we know it's fitting in its pocket, so there will not be any kind of issues. It'll also try and move around so that it doesn't basically collide with anything else. So if I look at this now, I can change the speed of which this basically changes. So every 5 degrees, show me the preview. So now I can increase the speed over here. I can change the AVI rate for the quality that I want to be able to export, maybe on a video. This record button allows one to do that, and you can save it WMV formats or AVI formats with a couple of little tweaks. You can go modify the quality. But here, repetitions, we can say how many times we want us to do it. So if I just rotate this by 45 degrees, which will be pretty quick, 4 degrees of 1 change, you'll see if I do 4 rotations, what will happen is it goes from the start to the end and continues like that. If I push play, it'll jump back continuously like this, unless I say start, end, start, which will then allow me to go and start and jump back from the end position to the start position. Okay, we have basic things we can go and modify like this. But what I want to do, instead of driving something like this, we can also drive mate constraints, meaning offset values. If I have an offset value sitting at 50, I can drive this to a different value as well. Being able to go and say drive, start position is 50, end this off at 150, and once again the same rules, we can go and play back and it'll move up and down. Now in this case, we're going to be breaking a specific parameter, which was our transitional one. So immediately it'll pick up things like that. It'll show you that you cannot actually drive that value unless this one has been defined as maybe suppressed or deleted. Yeah, and then we won't have these problems where we can move forward or backwards. Okay. So being able to drive constraints is pretty simple. And the nice thing about that is we see that if we drive something maybe from position here, so maybe there's an offset value between these, this could be quite interesting if we have to do this. I want to be able to move it from a distance over here, which let's say minimum value should be here, which is a value of say 25 moles. I want to make it 26 as the minimum. So I'm going to constrain this over here. I can even measure if I want to flush with this face and say, okay, that value over here can be driven from a 20 value over there to a 35 value. When I push play, you'll see that the movement goes in the area that has to travel. So let's go and push this up to say about 80. And we can see the travel going all the way along only the connected areas that I can go. Okay. But this in itself can also be modified to larger values. You can also see further playback and things like that. Okay. If it goes past the point where it cannot travel, it will once again bring up the error message saying it's going to override constraint, which it will not be able to do. But then we can simply say, move it back to that position, and we can very easily play back between the two values. Okay. Now, with drive constraints, we also want to be able to do this on multiple levels, on different assemblies. So we're going to look at that as well. We're going to drive a specific component to move other components. We also realize that when we do this, components themselves that are relative to one another can also then move. And like I mentioned before, the drive adaptivity, which can be toggled on. Now, what I want to do next is speak about the contact solver. The contact solver will allow for us to take something that we've looked at before, for example, that arbor press, and only be able to move components until they clash with other components part of that contact set. Now, it allows us to detect collision. It also stops us from moving components that are already intersecting. So it gives a couple of things that we can use for that, and also then go and see where is the interference between them. Now, the main thing that you have to realize is that there has to be part of a contact set, and the minimum of that is 2 components. And also we can then, or have to enable what we call the contact solver in order for it to then calculate them. Now, the bottom point, practical maximum due to processing speed, is something that one has to consider. You can't select every single thing and make everything in your assembly, especially if it's like 200-300 components, and make them all part of the contact set, and then activate contact solver. The problem is that the CPU has to calculate for every movement, so every pixel that you move an object, it has to recalculate its position to make sure that it's not clashing with anything. So if it has to do that with multiple components, it just reduces the time or increases the time it takes to calculate. So it means that you could move through an object without realizing that, because it's still busy calculating, you might not realize you've already moved through another object. So let's quickly take a look and see how that actually works when we go and use something like that. So I'm going to quickly jump to an example again. Let's go and look at that same arbor press. Over here, if I move this component through the other object, okay, I'm going to restore it to its resting position. Just go and say unsuppressed, move it back, and I'm going to toggle it off to be suppressed again. Now, if I make these 2 components as part of contact sets, I can right-click on them and add them to that category of contact set. Okay. It will still not detect that the one object is basically interacting with the other object if I had this toggled off, which in my case I already have on. Inside of inspect, we can go and enable or disable the contact solver. If it's off, you can still move to the components, but if it's been enabled, it'll stop when it connects to the other components. Now, what I was saying is if I select every single thing over here and add them all to contact sets, it'll calculate for every single thing that I want to move. And if it finds any kind of collision, so let's say, for example, it's interference with all these objects, maybe something over here is interfering with that, it'll stop movement over here. So that's also not a bad or good idea to be able to do stuff like that. So I'll just go and select these and try to remove them from the contact set. Okay. Well, now I'll disable the component. So if I go and just try that again, enable. Okay. Let's remove this from the contact set. I still might have some collision inside over here. Okay, so that's why it's, okay, there we go. So it's just that causing problems. But now when I have this on, see, contact solver is already on. Let's go and put this contact set over here on the RAM. Okay, so there is probably interference over here somewhere. Just want to do a quick selection. Let's try it like this. Wait, it's going to be hard. Okay, let's try that. Contact set off. Okay. Now, with this over here, there's still only a couple of components. But if I had to move faster than the CPU itself can process, I'll be able to jump straight through the actual component itself. Now, in this case, it seems like my computer is decent enough to run through the speed at which I'm operating. So it's not going to pick up any collisions or clashes that I cannot move through. I'll try to get another bigger assembly, which means I'll probably find some sort of issue there. Okay, but the idea behind this, once again, is it'll limit the movement of where it can collide with another object. So in the same way, if I had this was being able to rotate, and I put something through here, it'll be able to bounce and touch the object and then stop the rotations. Okay, so contact solver is very useful, once again, to try and free up your movement, that you can see how things move relative to one another. But problematic when you have things that intersect or interfere, especially if you have things like threading components, because there'll always be interference between contact sets when you have a component over here with another component over there where it's threaded into. You'll always find intersecting material because the threading being a visual property, so it's been modeled to the maximum size of the thread, so that maximum size now intersects with the whole size with its internal thread. Okay, so you'll always pick that contact solver will not work between threaded objects. Okay, just be careful of that. Okay, so what I want to look at next is now adaptivity. Now, this is something that one has to basically be careful for because it could be automatically applied when you're referencing components off of other ones. So when I model in an assembly environment and I create a part with reference to another object, it'll immediately be adaptive. Because if I project geometry off another component, and say it's a circular reference, if that updates to a new size, my component's reference has to also update to that new size, especially if I extrude it immediately from that same size. It knows it must also become bigger with the object that it's linked to. So adaptivity is always something that you'll see with these two arrows, the red and the blue arrow indicated over there. So if you see that, then you know that this is being adaptive. Now, sometimes we want to toggle that off, and it's simple right-click on the component to switch off adaptivity. But I want to show you the uses behind adaptivity because it's very, very nice if you want to enable this, especially when it comes to things like you see over here on the images. I want my spring to move with my component, even though this is now a fixed component or separate component. Okay, we'll look at another example of something like that. It's very, very fun to see how it works. But we also can use this information on different levels. I can override a value that I've specified as a dimensional value and make that value adaptive so that it can change freely based on constraint limits. Okay, so we'll look at that and see how we can actually use that. So let's really jump into an example. If I look at this over here. Now, in this case, let's say, for example, adaptivity was not on any of these components. Okay. So I take adaptivity off. If I change a mate constraint between two objects and update it to say a new value of say 200. Okay. It'll break that constraint because there's already things that are associated to it. So let's say, for example, I go and suppress that constraint now. And the alternative, which is on this one. Okay. Okay, it should be able to work now. Okay, still problematic. Flush, mate. Okay, it's probably one of these issues over here. Okay, but you see that I can go and override the value to new values. Okay, I can position them where I want to, but nothing in the model itself is changing, just positions. So if I want those changes to affect the actual model, and I want the model to update when I make these variable changes, then I have to make sure that my components, so if I go into, for example, the coil over here, that the extrusion that I maybe used to define that size, and what I did in this case, I simply just created a circular reference over here, so meaning a cylinder extrusion, and then in that extrusion, I made it adaptive, so that it knows that that value over here used for the extrusion can change. And then I used the coil command to generate a coil over here, making this an intersect option. So only where the object, the coil itself, will actually touch the cylinder will remain. Anything in between that will be removed. So when I did that, I know now that this in itself can be adaptive with its height. If I specify the coil parameters in the size area, height is an option that can change, which I call this extrusion's height value or extruded value a new parameter called height. Okay, so because extruded value over here, which I'll just quickly show you, let's just add this here. Okay, and we'll show this dimension as an expression. Okay, I've defined this height of the extruded cylinder as 100 mils, but I gave it a name height, which means in the coil, the actual height override was given that dimension value. Now I define 8 revolutions. I can even up this to say 10. It doesn't really matter for me because that just means I'm going to increase the number of the coils going around here. But the idea is if that is adaptive, I can go to my assembly and make this part itself adaptive within the assembly. And then when that is adaptive, I want this now to change in the height value at this offsets. But this cylinder itself in the center, if this was suppressed, it wouldn't be a problem. Okay, you'll see that I can go and override this value, say 200. Okay, it's still, sorry, it's not suppressed. If it was removed from the assembly, it wouldn't be a problem. So I'm not going to do that yet, because I want this cylinder itself in the center to also be able to change in its height value. So making sure that the cylinder itself, the extrusion, is also set to a value of 100 in this case, but it's also adaptive. Then I can make sure that the part's adaptive. So if I ever override this value, it'll automatically change that height. But the coil itself will still keep the same rotations, so you'll see that the height itself will start stretching it. So any kind of value that we override from here will affect the position and the rotations over here, like we see it over here. Once again, if we drop it down to 75, it also compress the springs that we see and keep that cylinder on the shorter level. Okay. Even if you didn't want that, you can simply delete that, and it will still keep the other overrides. Just say yes for now, I guess. Okay, if I change this value to 200, we'll see that the changes affect only the coil in this model. Okay, but I want to keep everything over here because I want to show you that if I drive this with a normal constraint tool, like we've done before, right-click and drive the constraint, I can enable in this drive adaptivity, which means go from 100 mil to a 200 mil size, and when I push play, it'll immediately extend it so you can visually see the changes as this coil extends or compresses. Okay, and we can keep that also going from a specific point to another point and bouncing backwards and forwards. So I'm just going to do this 3 times and change the step value to say every 5 mils make a step. Okay, and we'll see that it goes up and down and finally up again. Okay, now that is being able to drive adaptivity. So you might have heard of the term before, and now I get to visually see what we actually get to do with that. Okay, once again, a very nice thing to show with animations. Now, the last thing I want to speak about regarding the animations within an assembly level is the fact that we can go and use this information to connect multiple sub-assemblies to the main assembly. So it allows for 2 instances of an assembly to be in different positions, even though they're both flexible or the same component. They could be exactly the same, meaning instances, they're copies of each other, and they can be different completely within the assembly in their arrangements and movements. But we can also connect them via things like motion and transition that can make sure that these also maybe interact in the same way. So sub-assemblies also have to have this enabled, and anything in a lower level will also need flexibility enabled if you want it to move. So this in itself, just quickly want to show you a demonstration of this as well, because it's wonderful to see how the changes actually take effect on, let's say, for example, a higher level assembly. So if I look at something like this gantry over here, what I've done is inside of these rollers, I've already enabled each one to roll, and I've built in that motion constraint. So you'll see over here in the components, we have rotation. This component will rotate, which will cause this one to rotate, which will cause this one to rotate as well. But they aren't changing together with these ones. Because this in itself, because they're visually changing the component, which means this component in itself should also obviously be the same instance or new instance, so it'll also update in its rotations. But in the assembly, I cannot change the rotations. And this is because this is a sub-assembly within a main assembly. So when I'm in the main assembly, I cannot affect its positional change. So to do this, we have to make that specific assembly flexible. When I make an assembly flexible, I can go and select its components and move them, even though they are a sub-assembly of the main assembly. But in this case, it will not affect the movement of these components within the other sub-assemblies. So they're going to be unique. So if I want that one to rotate with this one, I also have to make it flexible. But what I want to show you is if I make it flexible, it's still unique. Because now this one can rotate, but so can this one, but they don't rotate together. Which gives me the freedom of saying when one should rotate. So if I go and do this, I can also then go back into normal constraints for motion, and I can go and select rotations and say, when I rotate this one in that specific direction, rotate this one in the same direction. So when I create this link, Now, both being flexible, if I change this one's rotation, it'll affect that one's rotation. Now, if I do this for all of these assemblies as well, it'll basically take place through all of them. And a quick way of doing this is just basically enabling the flexibility on each of them because they're not flexible yet. So I'm going to go and select this all the way down here and make sure that they're all flexible. And when I do that now, I can see individual ones rotate any of them, and I'll see their wheels will move. Okay. Now, with this, we can combine a lot of other options, especially if you want to show something like this gantry, and I want to show the conveyor system move along here while it's moving in a linear direction. I can have the wheels themselves move. So what I've done over here is I've pre-built this already. And I just want to show you when I go and open this, that if I have the actual conveyor system itself, and bear in mind that I didn't make this adaptive to change in size or direction, but if I did, when I go and use this, and you'll see, just to give you an example of what I've done, over here I've used that rotation translation on this face to say, as this face moves linearly, rotate the wheels using this rotation translation. And because they're all connected with the same motion constraints we've looked at before, which is this rotations over here, I can then see that flexibility will allow me to go and pull this while it moves all the wheels in a specific defined direction. If we look at these two, as I move the actual conveyor across, it'll move all of those wheels. Okay, and this basically itself can be left up to your imagination to see what you can define and what you can do to use these basic levels of, and some advanced levels of being able to animate your motion between your components within your larger assemblies. Now, if you want to record anything like this, one can bring all this information through to your Inventor Studio. Okay, so if you want to go to Inventor Studio, you can still go there and you can bring this information through here for higher visuals, for rendering and ray tracing, and your animations, where you can go and animate on a video the specific parameters that you've defined and set, for example, maybe an offset value between these faces to drive the animation completely with just a very quick parameter change. Okay, I'm not going to do that now, but it's very easy to go and do something like that to set up that. I just don't think we'll have enough time to actually get through one of these. But when we do that, we can then go and record this out with the rendering of the actual animation, and we're going to get a very nice high-quality visual of the whole assembly being driven from point A to point B, and even multiple cameras spinning around if you wanted to within this environment. Okay, so I hope that you guys enjoyed this. That concludes everything. We see that within this assembly environment, we got to look at the different types of animations. When we animate and simulate motion, we are basically allowing for static assemblies to move using a variety of tools depending on your application that you need to use. So within these tools, we looked at joints, constraints, the different motional types of constraints, being able to drive our constraints, and using the context solver to limit movement between components. And finally, how we can make within a larger assembly subcomponents adaptive, and also the entire assembly flexible with its subassemblies so that motion can be pushed through from all different levels of the assembly. Okay. So thank you very much for your time. I hope that you guys got to get something from the session. And please, if there is anything, please don't forget my email address. I'll put it back up again now for the front page. So you can email me at any time. And this session that I covered, just to mention, was already done by someone called David Ponka, which was a session that was hosted at Orange University. And if you want to follow the link, you can take this information down. Or you can even request from me just to send the information through for handouts and things like that that you can also use to try and go through it yourself as well.